Right. So welcome to the new lecture, and in today's lecture we'll discuss about the power measurement in AC circuits. So let us see what we had seen so far in the AC circuits. So in this three-phase system we deal about the star connected load as well as source. So I'll say star connected system. And mainly in star connected system, we had discussed about the line voltage and phase voltage relationship. Line voltage and phase voltage relationship. So what is the line voltage? So or you can say in either of the way, phase voltage is equal to VL by root 3 or VL is equal to root 3 times of V phase. This is for the star connected system, and the line current is equal to phase current. Remember one point here that I am talking about only the magnitudes. When we talk only about the magnitudes, these relationship holds good. If I want to say in phasor form, I can say the line voltage leads the phase voltage by 30 degrees. So this point also you should carefully observe, and that we had seen through a phasor diagram. And similarly, we also seen delta connected system. In delta connected system, we seen that the line current is equal to root 3 times of the phase current, whereas the line voltage is equal to phase voltage. Just quite opposite to the star connected system. But one important point here is that VL leads VPH by 30 degrees, whereas here the important point is that IL lags IPH by 30 degrees. These are the two important observations, especially for competitive exams. And one more point also we seen in the Y connected system, the neutral voltage. Usually we can write simply Vn. So Vn expression also very important. I am not writing the neutral voltage expression here, but you can recap. Okay, right. So having understood the three-phase circuits which are usually connected either in Y connection or delta connection. And what we are analyzing in this three-phase system is mainly the line and phase quantities. Line and phase quantities. So why are we doing this kind of analysis in three-phase circuit is that to get some kind of interested parameters which may be power, energy, etc. Now let us see in today's topic that how to measure the power in any AC circuit. And usually the power is measured by wattmeter. And let us have detailed understanding of the wattmeter. Then we go to the three-phase power measurement by using these wattmeters. Okay. So let us say that so wattmeter, the schematic diagram look like this. It contains mainly two coils where one coil is made of thick wire, very thick wire as like this. See, you can observe here I am intentional making thick and less number of turns. So this is one coil. This is one coil. So where coil is made with less number of turns but thick wire. And one more coil also there where it is made with very fine wire, thin wire but more number of turns. More number of turns. These are the two important elements in a wattmeter. One is the coil which is made of thick and less number of turns, and one more coil which is made with fine wire but more number of turns. Remember that whichever has less number of turns it contributes less impedance. Whichever has more number of turns it contributes more impedance. Okay. Now see that what is the names of these two coils. Let us see that. This first coil we call as a current coil. CC means current coil, whose terminals we usually represent as ML, whose terminals are ML. This is the symbolic notation that we will call the terminals of current coil as ML. And one more also there, that is CV. The second coil, which is made of more number of turns, we call as potential coil or voltage coil or voltage coil. As the name indicates that this current coil will try to measure the current, whereas the potential coil will try to measure the voltage of the circuit wherever we connect. Okay. So now let me put these things inside a box as like this, something. Now if I'll place this entire things inside a box, what could I see externally is that, what could I see externally is that, so these things are internally there which we could not see, the current coil and pressure coil or voltage coil. What we can see is only terminals, that external terminals. What are they? On the device they will write ML. Then you should understand that those are the two terminals which are brought out. Inside that there is a current coil. Okay. And one more thing is that the CV terminals, where CV terminals are the pressure coil or voltage coil terminals. Okay? Right. Now, for example, if I'll give some information as like this, which is visibly, so let me say as like this. If this current coil is something like this, current coil is I C in this direction, current coil current, and voltage coil voltage if I'll give as V CV, where C side positive, V side negative. Now this is a wattmeter. If I know current coil current and if I know voltage coil voltage, then we can write this wattmeter reading can be represented with the letter W, which is equal to voltage coil voltage magnitude. If you know the phasor form, so you take the magnitude of that into current coil current magnitude into cos of angle between theta V minus theta I. That is angle of the voltage minus angle of the current. This is what the wattmeter reading. Any wattmeter will read this value. That means if I know its corresponding current coil current and voltage coil voltage, I can write its wattmeter reading, how much it contribute, how much it show, the power is VI cos theta, which is the true power or active power, which we already discussed about this active power, which is equal to VI cos theta. You should understand what is V, what is I, what is cos theta form. V is the voltage of the pressure coil. I is the current of the current coil. But which are magnitudes, and of course these are RMS values of the quantities. Okay. So this is in generally any wattmeter reader. For example, just for example, to make get aware of this, how to read the wattmeter is that, for example, if I have a single phase load as like there is a load. Let us say the load voltage is given as like this. The load voltage is given as VL phasor and load current is given as IL phasor. They'll give some value. Let us say this is 230 at an angle 0, and let us assume that we know these things. Okay. And if the current is, let us say, 20 amperes at an angle of minus 30 degrees. These are the voltage and current. Now try to observe. If I'll connect the wattmeter over here as like this. If I'll insert the wattmeter here as current coil here where current coil is connected in series with the load where we need to measure the current. And let us connect the voltage coil in parallel to the load where we need to measure the voltage. Now, where I need the voltage? Voltage I need across this load. So from here to here I can join. See that? Now it is easily understood that voltage from here to here. This is what C, this is what the V terminals. Where C is connected? C is connected over here, C, and it is directly connected to the load. As because this has zero impedance, voltage across this is 0 volts. So whether it is connected over here or it is connected over here, it doesn't matter. Why? Because voltage drop across this element is 0. Okay. Now you should understand that CV voltage is equal to load voltage. Next, the current coil current, that is what ICC, is equal to load current. Now you could able to see what will be this wattmeter reading. So can you write this wattmeter reading? So in terms of some value, this is let us say wattmeter, and whose reading let us say W. Now what is the W? This is the generalized question. For which what you need to see is that in generally let me write in general wattmeter reading is equal to VCV magnitude ICC magnitude into cos of angle of the voltage minus angle of the current. Now I need to interpret this expression in such a way that what is CV voltage? What is voltage CV? C is connected to the load one side terminals. Let us say this is 1 dash. So 1 is connected to C and V is connected to 1 dash. Between 1 and 1 dash, how much is the voltage? VL. That means VCV is equal to VL. That you could observe here. Here, we need to interpret in this way that where CV is connected, is it connected across this load or some other load? If so, how much is its voltage? That we need to interpret. And where current coil is connected, is it connected in series with the load? If so, the series connected elements will have same current. So I can say load current is equal to current coil current. So in that way, we can interpret these things and we can get the required voltage and current to calculate the wattmeter reading. So ICC is equal to IL, which is equal to 20 at an angle of minus 30. Once I know the current coil current and voltage coil voltage, now it is easy to find what will be the wattmeter reading. So let us find the wattmeter reading now, as W is equal to how much is the voltage magnitude? 230 into how much is the current magnitude? 20 into cos of how much is the voltage angle? 0. How much is the current angle? So minus 30. So now simplify this and tell me the final answer, how much we will get this. So let me calculate these values. So the wattmeter will give 3983.7 watts, so which is the wattmeter reading here. So try to observe that clearly that how we get the wattmeter reading is that we should have clear focus on where current coil is connected, how much is its corresponding current. Usually current coils are equivalent to ammeter, so ammeters are connected in series with the element, so where we need to measure the current, so that corresponding current is equal to this current coil current. Similarly, voltage coils are analogous to voltmeters. Voltmeters are connected across the element to measure the voltage, in parallel to the element to measure that element voltage. So now just try to see what will be this CV voltage, that is voltage coil voltage and current coil current. Once we know these two, now it is easy to find the wattmeter reading. So if it is a single phase load like this, it is well and good, we can find directly wattmeter reading in this. And there are many trials and many people have so tried different things and they have come up with the optimal solution for three phase power measurement by using 2 wattmeter method. So let me write that. So 2 wattmeter, 2 wattmeter, sorry, 2 wattmeter method. This is very important. So try to understand carefully. It is so simple, but you need to understand little carefully. Okay. So for which, first let me take up a three-phase system. So for which I am taking some load as balanced load whose impedance is Z at an angle theta. Star connected load I am considering here. So another impedance Z at an angle theta and one more impedance Z at an angle theta. These are the three phase star connected load and it is connected to some, let us say, source as like this. Now what is our aim is, by using 2 wattmeters we need to measure 3 phase power. That means, so if I will consider this is R phase load, this is Y phase load, and if it is B phase load, we need to find RYB 3 phase load power, provided if we know some of the things as like this. For example, if it is BR, if it is BY, and if it is BB, which are phase voltages. VR, VY, VB are the phase voltages. Now, what is the 2 wattmeter method is that? So, straight away, let me draw the diagram, then I will tell you why we choose and such in such a way that. So, first, what I will do is that. So, usually we know that wattmeter consists of one current coil, one voltage coil. Okay. So, let me put those things first. So, I have one current coil here. And also I have its corresponding voltage coil over here. Okay. Similarly, let me take one more wattmeter. This also has one current coil, one voltage coil as like this. Now these terminals you can name as M, L, C, V as like this. Here also M, L, C, V. If you want, you can give suffix M1, L1, C1, V1. So M2, L2, C2, V2. Just to avoid the confusion. We have two wattmeters. Each wattmeter has current coil and voltage coil. Now the logic here is that how we connect this wattmeter is that choose any two phases, either of R phase and Y phase, or R phase and B phase, or B phase and Y phase. It's your wish. Any two phase lines. I am choosing for convenience R phase and Y phase. What I'll do is that I'll connect the current coils of these wattmeters in series with these two phases. See how I connected M1 L1 is in series with the R phase load. So as like this here, if I know the R phase load current IR, then I can say this corresponding current coil current ICC1 is equal to IR. That means this current coil is measuring the load current in the R phase. Okay. Next, similarly, you connect the second wattmeter also in any of the left out two phases. It's your wish. You can connect in any phase, no issue. So, now let me choose Y phase and I will be connecting the second phase second wattmeter current coil in series with the Y phase. So whose current coil current is equal to ICC2, which is equal to IY, which is equal to IY. Okay. Now the important task is that regarding the next connection, that where we need to connect the voltage coils is that the 2 wattmeter method states if we choose the current coils in R and Y, connect the voltage coils from those phases to left out phase. Those phases to left out phase. That means, so I'll connect here C1 to the M1, V1 to the left out phase. Which phase? B phase. In the same way, C2 to the Y phase and V2 to the left out phase, as like this. So this is what the 2 wattmeter method configuration. 2 wattmeter method configuration. Right? So now let me state that what is exactly 2 wattmeter method configuration is that. So in terms of words, I can write connect, connect, connect current coils, current coils, or let me write fully current, current coils of 2 wattmeters, of 2 wattmeters in in any of the 2 phases, or in any of the, or in series. Let me write here, just let me add one more word here, that in series with, in series, in series with any of the 2 phases, any of the 2 phases, and these are simultaneously, you should do carefully, that current coils must be connected in series with any of the 2 phases, and the voltage coils, the voltage coils must be connected, must be connected, must be connected from from those phases to, those phases means whichever I already chosen. Here for example I had chosen which phases, let me write in bracket here. So I had chosen R and Y. Current coils are connected in series with R phase and Y phase. From those phases to, from those phases to, from those phases to those phases means R comma Y to the to the third phase, third phase, which is B phase, B phase, third phase. This is the 2 wattmeter method generalized statement, that you can connect the current coils in any of the 2 phases. Voltage coils of those wattmeters must be connected from those phases to left out, or the third phase. Okay. So now just quickly let us have the phasor diagram for this star connected load, which we already seen in the last session. So quickly let me say that let VR is equal to, so V at an angle of 0, V means phase voltage, or you can write VP, it's your wish. VP means phase voltage magnitude, and I am considering balanced 3 phase and positive phase sequence supply. So VY is equal to VP at an angle of minus 120, and VB is equal to VP at an angle of plus 120 or minus 240, or Vp at an angle of minus 2. This is what the balanced positive sequence voltages. So these load voltages, that is VR, Vy, Vb, just I am considering as the balanced three-phase voltages. Once we know these things, can we find the load currents IR, IY, IB? So we can easily find these things as voltage divided by impedance. That is VR divided by Z at an angle theta, which is equal to VP by Z at an angle of minus theta. You can cross verify whether you will get this or not. Similarly, Vy divided by Z at an angle theta is equal to Vp by Z at an angle of minus 120 minus theta. And this Vp by Z can be considered as IP magnitude, phase current magnitude. So now IP at an angle minus theta, this is IP at an angle minus 120 minus theta. Similarly, the third phase Vb divided by Z at an angle theta can be written as Vp by Z at an angle of plus 120 minus theta, which is equal to IP at an angle of plus 120 minus theta. Once you know the phase voltages and phase currents, let me quickly put up these things in the phasor diagram, which is very important. Carefully observe. So I'll use the color coding. So for your sake of understanding carefully. So now, so this is R phase voltage. Next is Y phase voltage. Next is B phase voltage, which are VR, VY, VB. So let me write VB, VR, Vy. Sometimes I will leave, instead of writing these notations VR, Vy, Vb, I had used only magnitudes. So angles are defaultly understood. This is plus 120, this is minus 120. Okay, that is what Vb plus 120, Vy is minus 120. These are the phase voltages. Once you know the phase voltages, we already seen the line voltage concept. How we draw the line voltages? So for example, which line voltage I need, based on that I will try to proceed. Okay. First see that. So prior to that, let me put the currents also. Currents. So IR current lags the voltage VR by an angle theta. See, minus means clockwise direction. Clockwise angles are referred as lagging angles. So this is what the IR. What about IY? IY lags VY by theta. IY lags the VY by theta. This is IY. Similarly, IB lags the VB by theta. This is IB. These angles are theta. This is also theta. This is also theta. So, phase currents lag its corresponding phase voltages by an angle theta. That should be understood carefully. Okay? Right. Now, let us see that from this diagram, what will be these wattmeter readings? Let us say, this is one wattmeter which is kept inside the box as like this. This is one wattmeter. This is second wattmeter. And if I'll call this wattmeter as a W1, this wattmeter as a W2. What is the W1 reading? W1 reading is V, let me write here, V C1 V1 voltage into ICC1 into cos of angle between these. In the same way, W2 reading will be the voltage across C2 V2, which is V C2 V2, and current through the current coil ICC2 into cos of angle between this voltage and this current. Now let me write as it is these wattmeter readings first, then I'll think of what can be done. So I'll write as like this. So W1 reading is equal to V C1 V1 magnitude into ICC1 magnitude into cos of theta, let us say V1, V1 means VC1 V1, okay, that should be understood, minus theta I1, I1 means ICC1, okay, right. So similarly, what about W2? Magnitude of VC2 V2, magnitude of ICC2, cos of angle between this voltage and this corresponding current, okay. So don't get confused what is V1 angle theta V1 means theta VC1 V1. So that must be understood. So over a time we should be in a position to understand these generalized things. Why? Because if I use again V suffix C1 V1 it becomes too many quantities. Okay. Right. Now this is a generalized expression. Let me write in general. In general. Now your next observation should be more specific to this circuit. What is VC1 V1? What is VC1 V1? Where C1 is connected? C1 is connected to R phase. Where V1 is connected? B phase. So C12, let us say C12, C1 means R, R2 V1. Where V1 is connected? B. So R2 B is VRB. How much is the voltage? VC1 V1 is equal to VRB. In the same way, try to look very carefully where C2 connected to the Y, where V2 connected to the B. That means Y2B, VYB is the voltage of VC2V2 and VRB is the voltage of VC1V1. Okay, fine, well and good. We identified where C1 is connected and also where V1 is connected. So C1 is connected to the R phase, V1 is connected to the B phase. So R to B is the voltage of this coil. Up to this portion, I hope clear for everyone. Similarly, VC to V2. Up to this, I hope you should understand carefully. Next thing is, what about currents? See, where ML coil is connected, ML coil is connected in series with the R phase load. How much is R phase load? Current? IR. That means IR current is equal to ICC1. Where M2 L2 connected, whose current is ICC2, whose current is ICC2, then which is connected in series with the Y phase, so Y phase current is equal to ICC2. You should be in a position to identify these voltages and currents. Once we identify these two important things, now almost the power measurement concept is over as like this. So we seen that V C1 V1 is equal to VRB. Let me write here. Let me write here. Here, here. V C1 V1 is equal to VRB and ICC1 is equal to IR and here V C2 V2 is equal to, tell me, so where C2 connected? Y to B. So VYB and ICC2 is equal to IY. Now just after having this thing, try to observe that I need additionally VRB voltage, VYB voltage. If I know these voltages, I can write what is the W1, what is the W2. Why? Because IR is already known, IY is already known. IR, IY. But I don't know what is VRB and VYB. Now how can I write VRB? So that you need to cross verify. So after analyzing the connection, I came to know that I am in need of I am in need of I am in need of V V, let us say, what is that? RB, VRB. R2B means line voltage. So we need line voltages. Line voltages. Which line voltages we need to cross verify from the circuit diagram. Okay. So how you made the connection, that all depends. So now VRB, how can I write VRB? Can I write VRB as VR minus VB? Similarly, what is the other line voltage? VYB. VYB is equal to VY minus VB. How I am writing is simple KVL. See here. So if I start over here, then if I move in this way to reach the B, so VR minus VB. So arrowhead represents positive, non-arrowhead represents negative, like this. So plus VR minus VB is what? VRB. In the same way, VYB is, you need to move from where? Y to B. Start at Y here, then move towards the B as like this. In this process, see what are the voltages? Plus minus, plus minus. So plus VY minus VB is VYB. Now we already know VY, VB, etc. So if you substitute these things over here, you will get the corresponding things as root 3 times of VP, root 3 times of VP at an angle of plus 30 degrees. That what I said, line voltage leads the phase voltage by 30 degrees. Just substitute and cross verify whether you get this or not. Here also root 3 times of VP at an angle of Vy plus 30. How much is the Vy? So minus 120. So plus 30 is minus 90 degrees. So cross verify whether you will get VRB, VYB, these voltages or not. Okay. So now carefully observe what is the magnitude of VRB, what is the magnitude of VYB. Okay. So let me indicate these two things over here. VRB. In the phasor diagram, I want to indicate these two. So VYB, VRB means VR minus VB. So where is VR and where is minus VB? So minus VB I will sketch in this way with the dotted lines. So very carefully observe. This is what? Minus VB, minus VB. So now addition of these two, that is minus VB plus VR, which gives which gives which gives sorry, is that RB is not actually okay. Just carefully observe. So RYB fine. Okay, so R2B, yeah, fine, R2B, and this is Y2B. No issue, no issue. So this may not be so at an angle of 30 degrees. Actually, it may be a different angle. So let us verify slowly. So let us see that how much we will get. So here I'll get this thing as VRB phasor. And if you observe this, so carefully, so R2Y voltage is 120 degrees. That is splitted into half. This is what? 60 degrees. and half of that is what we are be making. So this is what 30 degrees. So here I will get actually negative 30. So don't say that. So like it's corresponding. Actually, it should be Ry. Vry leads the Vr by 30 degrees actually. But it is not Ry, so it is not leading, it is lagging. It is different line voltage. Just let me clear that point, that if it is Vry, like in the proper phase sequence form, that after R I should get Y, then after Y I should get B, then after B I should get R. Now in this way I can say as like this, Ry line voltage leads the R phase voltage by 30 degrees. Another point is YB line voltage leads the Y phase voltage by 30 degrees. One more point is that BR line voltage leads the B phase voltage by 30 degrees. Okay, but here it is not RY, so it is RB, that's why it is not leading by 30 degrees, it is lagging by 30 degrees. It is different line voltage. Okay, that you should carefully observe. Okay, right. I hope this also may be different. Let us see, we will see the what will be the angle. So I got VRB. Next task is VYB. So Vy minus Vb. So Vy is already here and Vb also there, minus Vb. Then angle between this, what this is what Yb, and now try to observe. Uh, so up to this is 60 degrees, this green color. So this is 30 degrees. So overall 90 degrees, 60 plus 30, and plus 30 if I'll add this one, so 120 degree. So now see that R2 means red color voltage 2, yellow color voltage is 120 degrees. Now is it satisfying or not? Cross verify. This green color is 60 plus 30 plus 30. So orally 120 degrees. So now the important concept will come over here, which is the angles. How much is the angle between VRB and IR and VYB and IY? So what angles I need is that carefully from the phasor diagram observe that angles between VRB and IR and VYB and IY. Tell me how much is the angle between VRB and IR? VRB is here, IR is here. So IR is making an angle of theta, but VR is making an angle of 630 degrees. So 30 minus theta is what between this? This is very carefully observed here. This gap is what the angle between IR and VRB. How much is that gap is? 30 minus theta. This is what very important concept. Many people will miss this. One is 30 minus theta. What about YB and IY angle? IY is here, VYB is here. So angle between these two is what this one, second angle. How much? 30 plus theta. So now once you will understand these points, that what will be the voltages, what will be the angles between the corresponding voltages, which voltages? Voltage coil voltages and current coil currents. Then almost 2 wattmeter method concept is covered. Now let us write what is the W1. W1 can I write as W1. How much is the voltage magnitude? Tell me. Root 3 into Vp. Can I write root 3 into Vp as VL? V phase is equal to VL by root 3. Right? So in star connection, V phase is equal to VL by root 3. That means root 3 into V phase is what VL. What about here? This also VL. But how much is this angle? Now I could able to say how much is VYB. VYB angle is, I can say, minus 90. Minus 90. I think this is correct. That what I got previously. Okay. Right. So voltage is VL, magnitude, into current is IP. IP is equal to IL. Yes or no? In case of star connection, IL is equal to IP. IL is equal to IP. So I am writing that IP, just instead of PH I am using P, which is phase current. So VLIP cos angle between VRB and IR. How much I got? 30 minus theta. And W2 also equal to VL IL. This is IP is equal to IL. Let me write everything in line quantities. Cos of how much is the angle between YB and IY? 30 plus theta. That's all. Once you observe these wattmeter reading, now it is easy to proceed rest of the things carefully. So what we do is quickly that. So let us add the wattmeters W1 plus W2. This is, let us say, equation number 1 and equation number 2. So equation number 1 plus 2. What I will get? Check it. So VL, IL is common. So in which? So cos of 30 minus theta. Another is cos of 30 plus theta. Expand these things and simplify this. Tell me how much we will get. So root 3, that is cos 30 into root 3 VLIL cos theta we will get. So am I correct? Check it. So if you want, just we can take one more step, VLIL. So cos of A minus B. So cos A cos B plus sin A sin B, right? Sin 30 sin theta. So plus cos 30 cos theta minus sin 30 sin theta. Just expand this and you will get. So some things will get cancelled. So sin will get cancelled. So cos 30 is root 3 by 2. So here root 3 by 2 is there. Root 3 by 2 plus root 3 by 2 is root 3. So that what we will get this root 3 cos theta, which is equal to root 3 VL IL cos theta. We already seen three phase power. If you remember, recap back to the previous lecture. Root 3 VLIL cos theta. What is it represents? It represents three phase active power. So if I'll add these wattmeter readings, I'll get the total three phase active power, which is very important conclusion. Then if I'll do some difference, that may be 1 minus 2 or 2 minus 1, it's whatever it may be. Let us see if it is W1 minus W2, what we will get. Check it. So VL IL, what I'll get here is that, so these sign terms will be there and minus minus will become plus sign, but cos things will go away. What I'll get? Sin 30 sin theta, but 2 is there, 2. So just cross verify. So this become minus. If it is minus, this cos will go away. So 2 sin 30 sin theta. So just cross verify that how much we will get this, and see that sin 30 is 1 by 2. So 1 by 2, 2 will get cancelled. So what I will get is VL IL sin theta. VL IL sin theta. Here straight away I got three phase active power, but here I am not getting straight away three phase reactive power. What we know is three phase reactive power, which is Q three phase is equal to root 3 VL IL sin theta. This is what the three phase reactive power. But out of that, which quantity we got is only this portion by subtracting the 2 wattmeters. So if I'll multiply root 3 by the subtracted values, that is W1 minus W2. Why? Because VLIL sin theta is W1 minus W2. So root 3 W1 minus W2, what does it give? Three phase reactive power. Three phase reactive power, which is very important conclusion. And one more thing which is important is the power factor. So try to observe these equations. So let me say this is third, this is fourth. From equation number third and fourth, we can get some more important information, that theta value. If I'll divide 4 by 3, what I'll get is that VLIL sin theta is equal to, so W1 minus W2, and here from third equation root 3 VLIL cos theta, from third equation here I'll get W1 plus W2. Okay, 4 by 3 equation, it gives this. Try to observe VLIL goes away, sin by cos is tan theta. Bring the root 3 to other side. So root 3 into W1 minus W2 divided by W1 plus W2 is tan theta. Once you know W1, W2, you can calculate tan theta. Once tan theta is known, we can find the theta also. Theta is equal to tan inverse of this entire value. Tan inverse of this entire value. So that we will get the what? Important information about the power factor. What is power factor? Cos theta, which is equal to power factor. So once we know that, so we can write cos of this entire value, which is tan inverse of all these information. So that is what the power factor. Okay. So up to this is enough about the three phase power measurement, and these are the three important factors which are active power. How much is the active power? Which is W1 plus W2. How much is the reactive power? Root 3 times W1 minus W2. This you should not forget. Many people in a hurry, they'll say that W1 plus W2 is active power, W1 minus W2 is reactive power, which is wrong. Root 3 times of W1 minus W2 is reactive power, and power factor is tan inverse of this and cos of that, what it gives the power factor. Just quickly see this problem and let us wind up the things. And here just I hope some more things you need to do uh, to solve this problem, or let me spend some time on this. Let us see that this is a three phase balanced load and has impedance of this much. Okay, and the load is connected to 208 volts, and predict the readings of W1, W2, total three phase power, active power and reactive power. So let me quickly put up these things over here. So what I will do is that first you need to make the calculations of all the phase currents, line voltages, phase voltages. Then you can get what is W1, W2. Okay. So for which just let me give the clue. Here they used ABC system instead of RYB, whatever may be the thing. I will tell you in this way. The given voltage is line voltage, 208 volts. Immediately I will say it is star connected, so Vp is equal to 208 by root 3. Next, immediately what I will say is that this is A phase voltage, this is B phase they considered here, and C phase they considered here. No, whatever may be the thing, no issue. Right. So otherwise, yeah, some extent it's okay, but I want what I need is anyhow these things also needed. That's why just I am trying to write A phase voltage. I can write as Vp at an angle 0, which is equal to 208 by root 3 at an angle 0, and Vb is equal to Vp at an angle minus 120. Observe that I am using positive phase sequence. Positive phase sequence. They had given here load configuration in different way. It doesn't matter. Source I am assuming as positive phase sequence. So you substitute what is Vp here. Just I will give the basic guidance. If not, I will solve completely in the next class. So Vc is equal to Vp at an angle plus 120. Plus 120 degrees. Once you get these three phase voltages, what I will do is that I will calculate Ia. Ia is equal to Va by Z. How much is Z? They had given, see here. You can convert that into polar form. So Zy, which is equal to, let me write here somewhere, Zy is given. Zy is given 8 plus 6j. Okay. So next is Ib, Vb divided by Zy, Ic, Vc divided by Zy. I got the all phase currents. Next is which voltages I need, for which I will check the wattmeter connection. So wattmeter voltage coils are connected, see where to where. This is one terminal of the wattmeter which is C1 equivalent, another terminal is V1 equivalent here. C1 to V1 is VAB, and this is what C2 equivalent, and this is what V2 equivalent. V2 is connected to B, so VCB is another voltage. So what I need is VAB is equal to VA minus VB. You calculate how much is that. We know VA, VB, VC. VCB is equal to VC minus VB. Substitute these values, you will get some value. Once you get VAB and VCB, IA and IC, now I can write wattmeter readings as like this. W1 is equal to VAB magnitude, whatever you get here, whatever value you will get here, into IA. This current is ICC1 is equal to IA. See here. This current is ICC2, which is equal to IC. So this is Ia magnitude into cos of angle of VAB minus angle of Ia. Once you know these values, you can get W1. Similarly, W2. W2 is VCB magnitude into IC magnitude, right? Is that IC? Yes, IC into cos of angle of VCB minus angle of IC, only angle. Once you get W1, W2, now tell me what is total three phase active power? PT is equal to P three phase is equal to W1 plus W2. And what about QT? QT is equal to Q three phase is equal to W1 minus W2, but additionally you need to put into root 3. So these tasks you complete. I had given all the formulas, just substitutions are left out. So try to work on these things so you will get better understanding of this three phase power measurement. Okay. Thank you all.